Okay, so section 8.4 deals with the determinant of a matrix. We're first going to kind of talk about what that looks like for a 2 by 2, and then we're going to use a formula to sort of define some notation and get you guys used to some notation. And then we'll finish with some applications of the determinant. So for now, it's just going to be kind of this thing floating around, but later on we'll look at some applications of it. So initially, the determinant was used in order to help find inverses. So let's talk about let's say we're given a 2 by 2 matrix A. And I'm just going to say it's the matrix A, B, C, D, where those are all numbers. Now it was determined that, well, this whole, when finding the inverse, the whole AD minus BC seemed pretty important. And I think at the time they really didn't realize how important. So this was what we had for the inverse, but what I want to focus on here is this AD minus BC. So if we're given a 2 by 2 matrix A, then the determinant of A, let's go back to the color coding here, the determinant of A is this number A times D minus B times C. So notice that this is just now a single number. So the determinant is kind of a way to take a matrix, which is an array of numbers, and boil it down to just a single number. And while this doesn't give us all the information about the matrix, it can tell us quite a bit. So the determinant can tell you quite a bit about a matrix by becoming just a single number. Notationally, you'll see this in a couple different ways. Oftentimes you'll see det of A, or you'll see something like this. So it looks like the brackets we usually use for a matrix, except it's more like an absolute value symbol. Or you'll even see something like this. So you'll see the matrix, but you'll just have an absolute value around it. So all of these are fine. For example, if I said let A equal, let's go back to, I don't know, let's do 5, -3, 8, and let's go with 2. Determine the determinant of A. You'd say, well, I just have to take the determinant of A would just be 5 times 2 minus -3 times 8. So we would have 10 plus 24, which would end up giving us 34. And that would just be the answer. So with a 2 by 2, it is pretty straightforward. Now, one of the key results and the key reasons we use determinants has to do with inverses, like I mentioned before. So let's go back to the definition for A inverse. It was 1 over AD minus BC. Now notice this is actually 1 over the determinant of A. If the determinant of A was 0, this would be bad, because now we would have 1 over 0, which would be undefined. And so this actually leads to a result, or a definition, I guess you could call it, on when an inverse exists. So in the previous section, we talked about inverses, but I didn't really discuss what happens if an inverse does not exist. We just assumed it always did. And now we know that if you are given a square matrix A, then A inverse exists if and only if the determinant of A does not equal 0. So if the determinant is 0, then the inverse doesn't exist. And this works for all square matrices. It's not just for a 2 by 2. So we don't really have a formula for the 3 by 3 situation, but the same holds true. If the determinant of A equals 0, then A inverse does not exist. Okay. All right. So that's a great result. We have that now. Let's get into a bit more of the nitty-gritty here in terms of notation. Now, part of the reason I like to do this in this section is really just to help train your brains to kind of think mathematically and understand mathematical definitions when they come up, because this will come up throughout your career. Potentially, if you're in engineering or the sciences, you will have some pretty lengthy definitions to get through. Maybe not necessarily math, but you will have to make sense of what you're thrown. So here is a couple of, we'll call them definitions, and it has to do with determinants. So we found the determinant for a 2 by 2. What if A is bigger than 2 by 2? It's not so simple. We don't just have kind of these nice, easy formulas. So here, we're going to define minors and cofactors. So in order to do this, we're first going to let A be a square matrix. So once again, that means n by n. We're going to define the minor, which I'll call Mij, is the determinant of the matrix which is obtained by deleting the ith row and jth, whoops, one sec, I don't like that, and jth column of A. So we'll start with that, and then I'm also going to define the cofactor, and then I'll give you an example of what I'm talking about. The cofactor is C for cofactor, and this is going to equal -1 to the power of I plus j times the minor. So first we're going to define these. Now I'm going to give you an example, and then we'll get into the actual definition for determinant. So as the example here, let's just say you have a matrix. We'll be using this one later as well, but let's say it was 5, 0, -3, 0, 12, 4, and then 1, 6, 3. If I wanted, let's say I wanted to find, let's do M1, 2. So if I was doing M1, 2, I would be looking at the matrix. Let's rewrite that one to start with. So I'm looking at the first row. I'm going to delete the first row and the second column. And so then I'm left with the determinant of the matrix 0, 4, 1, 3. So this would be 0 times 3 minus 4 times 1. So I'd end up with -4. That would be the minor. If I wanted to find the cofactor of 1, 2, then I would take negative 1 to the power of 1 plus 2, and I would multiply that by negative 4. Now negative 1 cubed is just going to be negative 1, so I would end up with positive 4. If I wanted to do, let's say, let's do M2, 3. This would be the determinant of the matrix 5, 0, 1, 6. So this would end up just being 30. The cofactor of 2, 3 would end up being negative 30. Okay. Now we're ready to define the determinant. So the determinant of any square matrix is given by the sum along any row or column. So I'm going to just use 1 up to n of a 1j times the cofactors 1j, where that 1 can actually change, so I could actually do so I'm still going to go, but I could say instead of using the first row, I could use the second row, etc. Or if I wanted, I could actually use the columns instead. I could say the first column now. So this is a pretty detailed formula. Really what this is saying is it's the sum of the entries in the matrix times the cofactors. And you can do that along any row or column that you like. And I'll show you what this means in practice in just a moment. And I think we'll stick with a 3 by 3 here. So let's go straight into an example. Find the determinant of the matrix we were just looking at. 5, 0, negative 3. Okay, so here's what this formula is really telling me. I can either choose any row I want or any column I want. And so once you pick one, usually I like to pick one with zeros in it. It just makes things a little bit easier. But you're going to pick any row or column. So let's just choose row 1. I'm going to write down the terms in row 1. We have A11 is 5, A12 is 0, and A13 is negative 3. Now I need the corresponding cofactors. So I need C11. So this is negative 1 to the power of 1 plus 1 times the minor, 1, 1. I need C12. And I need C13. So let's go ahead and calculate these minors. M11 is the matrix, or the determinant of the matrix 12, 4, 6, 3. So 36 minus 24, which is just going to give me 12. The minor 1, 2 is going to be the determinant of the matrix 0, 4, 1, 3, which will give me negative 4. And then the final one, the first row and the third column getting deleted, is going to be 0, 12, 1, 6, determinant of this matrix, which is just negative 12. Now what we're going to do is take the sum, so A11 times the cofactors, and add these together. So it still is a lot of work, but really this is what that formula is saying up here. When we're finding the determinant, we're taking the sum along any row or column that we like, and we're taking basically the sum of three different terms. So A11 was 5, and then the cofactor is just M11, which was 12. A12 was 0, so that's just going to go away. And then A13 was negative 3, and the minor is negative 12. So I end up with 60 plus 36, so I end up with 96.